everyone. We're very happy to have Chao Li here with us today, and he's going to be telling us about the stable Bernstein problem for minimal hypersurfaces. So please, Chao, whenever you're ready.
Okay, thank you. Yeah, so this is going to be the continuation of a talk I gave here 1.5 years ago. So I'm kidding. I'll start over. Okay. I'm going to talk about a particular problem called the stable Bernstein problem for minimal hypersurfaces. So I'll try to, in the first half hour or so, try to motivate the problem, starting with some history. So I think all these kind of problems really go back to the classical Liouville theorem. We all learned in complex analysis or analysis. So if you have an entire solution to entire harmonic function, so C2 or right, bigger? Okay, yeah. Soup. An entire function which is harmonic and bounded, then U is constant. Okay, so it's of course a classical theorem, and then Bernstein was basically thinking about a similar rigidity problem for other type of PDE, and a theorem that he claimed, which is correct, is that if we consider the entire solutions to the so-called minimal surface equation in R2, so U is, say, a C2 function on R2, solving the following nonlinear equation. So divergence of the gradient over square root of 1 plus gradient square equals 0. Okay. So this equation is called the minimal surface equation. Let me write MSE for it. Okay, so if you have an entire solution to the minimal surface equation, then U has to be affine. So in other words, the U of x is AX plus B, basically. Okay. Now, this minimal surface equation has a geometric meaning. So this equation is equivalent to asking that the graph of U inside R3 is a minimal surface. All right, so geometrically, a surface being minimal, let me make such a definition. So generally speaking, let's consider a sigma n contain R Euclidean space, maybe of a much higher dimension. Then sigma is called minimal if and only if the first sigma is stationary for the area function. Also, ddt of you take any variation of sigma, so the volume of sigma t at t equal to 0 is 0. This for every variation. So it's the critical point for the area functional, and equivalently, this is also saying the mean curvature vector h on sigma identically vanishes. Okay, so actually the mean curvature vector of a graph is basically given by this divergence from operator. Okay. All right, so Bernstein claimed the theorem in 1914. He had a very interesting proof. Nowadays, we understand the proof a little bit better. On the other hand, his proof is very restrictive to 2 dimensions. And his original proof was not entirely correct. It was corrected by Hopf, and the analysis Hopf in the 1940s. Okay, now I'll not go into his proof, but rather, since his proof only works for entire solutions on R2, he asked the following, I guess, well-known Bernstein problem. So basically, prove a similar statement. for solutions to minimal surface equation, well, U for U, let's say. And U is entire inside Rn. We'll construct a counterexample, a nonlinear solution to the minimal surface equation. Okay, so this is the classical Bernstein problem, if you like, for the minimal surface equation. Okay, now, of course, then people try to study this problem. And the starting point, which actually, well, let me maybe first put a comment that, the study of Bernstein problem, or generally the minimal surface equation, I think has motivated a lot of developments in geometric measure theory and, modern techniques in nonlinear PDE, at least nonlinear elliptic PDE. And a crucial and first step was due to Fleming. And so it's this was in 1962. So Fleming gave a different proof of Bernstein's original theorem in R2, using a more modern approach, so different proof. And his proof is more, geometrically natural. So it is based on the following so-called monotonicity formula. So for the monotonicity formula says that for every minimal surface embedded in immersed in Rn, if you look at the volume, the n-dimensional volume of sigma inside a ambient Euclidean ball of radius rho, centered at any point, that's centered at 0, and then divided by rho to the nth. So rho to the nth is the growth rate of Euclidean ball of that dimension. So this quantity is always increasing in rho. Okay, so this is a celebrated monotonicity formula for minimal surfaces. And the second point is that that's the first key point for Fleming's for Fleming's proof. Well, the second key point is that actually, if you're a minimal graph, then this number is uniformly bounded above. So the second key point is that a minimal graph, if sigma is the graph of a function u contained in R3, let me write R3. Then, well, a simple calibration argument shows that being a minimal graph means that sigma is actually error minimizing. This means for any compact portion of sigma, that compact portion minimizes area among all surfaces with the same boundary. Okay, so it's a stronger condition than just being a critical point, right? It's just minimum, all right? So in particular, let's see. So I have let's say a minimal graph inside R3. What I can do is that I can compare, for instance, I can intersect it with a big ball of radius rho. Okay, so this is B rho at 0. Now, let's say for at least for large enough rho, this minimal graph will intersect the sphere and divide the sphere into two components basically, right? Now, at least one component has area as large as half of the sphere's area, right? And now sigma is error minimizing. So in particular, this tells us that if we just compare the portion of sigma inside B rho, this is going to be less than half of the sphere's area. Okay, so 2 pi. Okay. 2 pi rho square, I'm sorry. All right, so just comparing to half of the sphere's area. Now, combining these two statements, okay, so you have a monotone quantity which is uniformly bounded from above. This tells us this monotone quantity actually has a finite limit. Okay, so that finite limit, so this means the limit rho goes to infinity, volume of sigma intersecting b rho over rho squared, this exists. And moreover, by looking at the, by some kind of compactness for minimal surfaces, where, we need to, technically we need to enlarge the class of objects. It's like when solving a PDE, we look at the subspace of weak solutions. So the weak solutions for minimal surfaces are called, for instance, integral currents or minimizing currents. But in some appropriate sense, one can take a limit as sigma goes to infinity, as rho go to infinity of sigma rescaled by rho. So that limit has to be, and the limit rho inverse of sigma intersecting b rho. Well, maybe just let me write rho inverse times sigma. So this limit also exists.
What's rho inverse again?
Oh, if you want, that's just the rescaling of
By rho, not rho squared?
By rho, not rho square, right? You're geometrically rescaling a surface.
Oh, I see.
Yeah. So this limit exists, and the limit should be a cone. An error minimizing cone, let's say. So this cone structure comes from analyzing the equality, the equality case of this increasing function. So whenever this is a constant, sigma has to be a cone. Okay. All right. So let's code this minimizing cone by C. Okay. So the observation by Fleming is the following. Now, it's a basic fact in differential geometry in R3. If you are a cone and you are minimal, you have to be a plane, right? Because on cone, one principal curvature is 0. Now minimal tells you that sum of two principal curvature is 0, so the other has also to be 0. Okay, so C is in R2. Sorry, C is a two-dimensional cone, minimal cone in R3 tells you that C is flat. And in fact, by this array bound, one can show that C is actually a multiplicity 1 plane at infinity. So on the other hand, at tiny scales, sigma also is looks like a multiplicity 1 plane. So if at scale 0 and infinity, there sigma both look like the same kind of plane. Sigma has to be plane itself. Okay, you have equality case in the monotonicity formula. Okay. So one kind of a lot of ideas in this Fleming's original different proof extends to higher dimensions. Now there are some non-trivial parts. Essentially, if you can prove that in Rn plus 1 you're an area minimizing cone, any area minimizing cone has to be flat, then you essentially solve the Bernstein problem in that dimension, right? So the only different thing that changes along the proof is this part. Okay. Okay, so the next step after Fleming's original proof was due to Di Giorgi. So when n is 3. Well, Di Giorgi doesn't quite classify cones, higher dimensional minimizing cones at this moment. On the other hand, he had the following observation. So if you have a nonlinear solution to the minimal surface equation, then this cone C has to split off an R factor. So for some minimizing cone K in one dimension lower. Basically, the observation is that if the solution is nonlinear, then it grows too fast, superlinearly. So that if you rescale down a graph of, say, a quadratic function, then this xn plus 1 direction will split off. That's more or less what happens. Okay? So this means that we gain one dimension for free. If you classify error minimizing cones k in Rn, you get the answer, affirmative answer to the Bernstein problem in Rn plus 1. Okay, so particularly minimal cones R3 are all flat. This tells us that solutions to the minimal surface equation over R3 are also flat. Okay, so one dimension for free. And now the question really boils down to classify error minimizing cones in Rn plus 1. So then basically this was done in a famous paper by James Simons. So let me just write down the theory. So this is when Almgren first did it for n is less than to 4, and the Simons when n is less than to 6. So the conclusion is that suppose k inside Kn is n-dimensional minimizing cone in Rn plus 1. Well, actually, their proof both work for the notion stable minimal cone. I'll explain this word in a minute. Then K is flat. Okay, so their analysis is actually based on the notion stability. So let me define it. So let's consider a minimal surface. So by definition, that means the first variation of area is volume is 0. So it's a minimal immersion is called stable if the second variation is non-negative. For every variation sigma t. Okay. So apparently, if you are minimizing, then you're automatically stable. So stability is like the second derivative test in variational problems. Okay.
And for cone, you're only applying this out the way of the origin.
Oh yeah. Right. Okay. And actually, this result is sharp because in let's see in R8, so in R8, one has the for instance famous cone which is sometimes it's denoted by C33. So that's the Simons cone. Okay, so it's given by this quadratic relation between coordinates. It's a homogeneous relation, so it's a cone, it defines a cone. And this cone turns out to be minimal and stable. Okay, now of course it's non-flat. All right, and in fact, Bombieri, DiGiorgi-Giusti so this was done in the Simons result was in 68, and 1 year later, Bombieri, DiGiorgi-Giusti showed actually this cone is not only stable, it's actually error minimizing. So combining all this knowledge together, we have a complete answer to Bernstein's problem. So the answer is an entire minimal surface solution, entire solution to the minimal surface equation is flat if and only if when n is less than or equal to 7. Remember, we gain one more dimension because of the DiGiorgi result. Okay, and the false, there are counterexamples when n is at least 8. Okay, so there are nonlinear solutions to the minimal surface equation in higher dimensions. That's also constructed in the Bombieri, DiGiorgi-Giusti paper. Okay, so at this moment, we essentially just closed the Bernstein's problem entirely. It's a purely PDE problem, but the solution is somewhat geometric, and it boils down to the cone classification problem. Okay. Any questions so far? Okay, great. Now, as geometers, we usually want to work with a more intrinsic notion rather than asking that a surface is graphical, for instance. Graphicality doesn't always make sense in Riemannian manifolds, right? So there goes the natural extension would be the so-called stable Bernstein problem. Namely, we want to prove a similar rigidity statement for, let's say, minimal surfaces that are not necessarily solutions to the minimal surface equation, but rather let's give a few assumptions, well, intrinsic assumptions on the minimal surfaces. Okay, so the problem states the following. So let's suppose, Mn is sitting inside Rn plus 1. Well, rather, let's view it as an immersion. So this is a complete two-sided stable minimal immersion. Then try to prove or disprove that M is flat. Okay. So all these assumptions are naturally satisfied if M is a graph. Okay.
You say about two-sided?
Yes, two-sided here means that there exists a globally well-defined unit normal. So in this case, it's equivalent to orientability. Okay, it's equivalent to orientability. Okay, again, all these assumptions are automatic for a minimal graph. Okay, so now.
For people that don't really think much about smooth manifold immersion, means it's locally an embedding, right? So
Okay, take it to be an embedding if you want. Right, locally embedding. We could a priori allow self-intersections, for instance. Okay, anyway. All right, so such a statement would be, well, very useful in geometry, I would say. For instance, it's a common feature in a lot of nonlinear PDE, right? So if you have a global rigidity result like this, there is a corresponding local a priori estimates, C2S estimates. In this case, the equivalent form as in local estimates is the so-called curvature estimates. So the curvature estimates, which is equivalent to the stable Bernstein theorem, is the following. So take any x m plus 1 g. Let's say it's a closed Riemannian manifold. Then any stable minimal immersion satisfies the a priori estimates that the curvature of this immersion at any point is less than or equal to some constant that only depends on the ambient space. Okay. We can quickly see in this case why such a curvature estimate is equivalent to the Bernstein problem. For instance, the easy case is I can actually allow boundary to happen. So if the surface has boundary, then I just multiply the distance. Okay. For instance, to deduce the Bernstein theorem from curvature estimates, we take X to be the Euclidean space itself. Right? Then suppose you have a complete minimal immersion, then you can take larger and larger geodesic balls of this immersion. Okay. Then for any fixed point X, the distance by taking the immersion to be larger and larger geodesic, by considering larger and larger geodesic bow, this distance is going to infinity. Okay. So for any fixed point x, the curvature has to be 0, and that's yes.
What sort of curvature does the symbol AM represent? Is it
Oh, so that's the second fundamental form of the immersion. I'm sorry. So this is the second fundamental form. Okay. Yes. All right. And by the way, the second fundamental form by Gauss equation dictates all the intrinsic curvatures as well. You can take Riemann curvature tensor on M, for instance. That's also fine.
So since this is a colloquium, you want to try to reach a general audience, you want to say this is, you're taking the sum of the squares of the principal curvature.
Oh, yeah. Yeah, this is the square. These are the principal curvatures, and it's really A is really a matrix, and you are taking the square norm of L2 norm of the matrix. Okay. All right, and to deduce the Bernstein property from curvature estimate, you just take X to be Euclidean space. The other direction is a little bit more involved, but that's essentially a proof by contradiction argument. You can't have arbitrarily large curvature concentration along a sequence of stable minimal surfaces. Okay. Otherwise, basically, in the contradictory limiting picture, you would get a non-flat two-sided stable minimal immersion in Rn. It's some kind of Euro argument. Okay, but now one can imagine that this kind of curvature estimates are powerful for minimal surfaces and related topics. So let's see what we know so far for the Bernstein. So one stable Bernstein. So one quick remark is that this Bernstein problem is false. The answer is negative when n is at least 7. So here I assume everything's in immersion, so that counterexample is modeled on this Simon's cone. So it turns out that the cone is a singular. It's not immersion, singular at the origin, but you can actually find the smooth minimal immersion embeddings, modeled on this Simon's cone. So it's a smooth perturbation of the cone. Okay, and those are complete two-sided embedded minimal surfaces, but are non-flat. Okay. So it's false when n is at least 7, and previously it's known to be true when n is 2. So this was done independently by Fisher, Cobray, Shane, and Docamo, Peng, and Pogorev at around the same time, basically 1980s. To try to explain the proof a little bit, I need to write down the stability condition a little bit more explicitly. So the stability condition in this case where you have a minimal submanifold of codimension 1 inside Rn, which is inside Euclidean space, for that to be stable, the surface M should satisfy the following so-called eigenvalue type conditions. So for any compactly supported function f, the f should satisfy this condition. Okay, so for every compactly supported function f. Okay, so again, A here is the second fundamental form, and here I'm taking the square norm of that second fundamental form. It's, again, imagine this as a matrix. Okay. All right. So this condition is satisfied for all f. That's it's an eigenvalue condition. So first eigenvalue of minus or plus and minus a squared is larger than or equal to 0. Okay. Okay, so when the dimension of the surface is 2, there are some really powerful things that powerful tools one can use. So when n is 2, it turns out that a squared is just minus, let's see, twice Gauss curvature. Okay, so that eigenvalue condition is actually a condition on the Gauss curvature, and that condition, lambda 1 minus plus and plus 1/2 k non-negative. So remember, that's the stability condition in this case. So this is actually conformally invariant if you want. So then, if you read the first two proofs, the Fischer-Covray-Shen proof or the Docamo-Peng proof, they use complex analysis, by uniformization theorem essentially. Okay, so the first two proofs are with the complex analysis. And the third proof by Pogorelov there is also really just a two-dimensional proof, but he uses Gauss-Bonnet instead. So here's, let me just write here with using Gauss-Bonnet. I'll try to get back to this third proof a little bit, in 10 minutes or so. Well, but in any case, you see these two proofs are really two-dimensional, right? Really restrictive. Okay, so now how about extending to higher dimensions? So starting from the dimension n is between 3 and 5. So remember, ideally we would want to go to 6 dimensions also, right? So okay, so this and there's an important theorem by Shen, Simon, Yao. Which says that the statement is true provided your minimal surface satisfies another assumption. Namely, one can compute the volume of the intrinsic ball divided by rho to the nth. So notice that in the monotonicity formula that I probably already erased, we're taking the volume of the intersection of M with the ambient ball. On the other hand, the Shen-Simon-Yao assumption is a little bit weaker, so it's looking at the volume of the intrinsic ball somehow. Okay, so this quantity doesn't really satisfy any good monotonicity property, but instead they assume that this is finite. The volume growth, intrinsic volume growth is finite. Okay, so if you know this volume growth is finite, then that's also true in these dimensions. And their proof is also really, really great. So the basic idea is to use a Moser type iteration scheme to upgrade from the L2 stability inequality to an LP. If you can do it for Ln, then basically you're done with this assumption. And there's a really nice iteration scheme there. Okay, so remember we're missing one dimension here. So when n is 6, it's also true. It's done by Shen Simon originally, and if we assume assuming this volume growth and embeddedness. So for embedded minimal surface with stable minimal surface with the volume growth, it's also true. Maybe let me just say this in words. Actually, just last year, Constanti Bellatini proved a similar statement, a stronger statement when n is 6. Basically, you should without embeddedness, but you need to assuming the extrinsic ball growth condition instead of the intrinsic one when n is 6. He proved a little bit stronger statement in this dimension. Okay, anyway, so let me tell you some stories about recent progress on this stable Bernstein problem. by the way, I'm just picking up some, I just showed you some classical results, but there are really lots of people working on this stuff and lots of partial progress before. So what's known now is that it's true without any other assumption when n is between 3 and 5. Okay, so let me briefly tell you what happened. So when n is 3, we had 3 different proofs, totally different, entirely different proofs. The first one was done by Otis Chodos and myself. Second one was also due to us, and then also the third proof was due to 3 Italians, Catino, Mastrolia, and Racconrani. Okay, 3 different proofs. The gist is okay, and we did it in 2021 first, and then the second proof we found in 2022, and their proof was also in 2022, and we were stuck because they all seem really restrictive to dimension 3. But last year there was an observation, so we did it in dimension 4 with Paul Minter and Doug Stryker. These 2 are at Princeton. I understand that I think they were having fun in a bar, and suddenly some idea pops out, and we did it. And these proof were then after this work, I believe several groups of people in the world started working on the extension to n equals 5, and finally it was done by Mazet. Okay, so and this happened last summer, basically. Okay, so now it's a great time to wrap up and think a little bit about what's behind these proofs, and so which I'll tell you about in a minute. Okay.
So is n equals 6 still open? If you
Yes.
with additional hypotheses?
Oh, I mean, if you assume nothing, it's open. If you assume something like these plus embeddedness, or immersion plus the extrinsic volume growth, that's done. Yeah. Okay. So, and the 6 is open.
It's not monotonicity, it's just
There's no monotonicity for this intrinsic volume growth.
the extrinsic.
Extrinsic, yes, there's a monotonicity. Yeah. So if you assume that has a uniform upper bound, then it's done. Okay. So it's open. So NS6 is the last open case. Okay. It's quite hard, I think. Okay, so the starting point of the story was, our proof was the following. So, sorry. Before that, I need to tell you 2 basic reductions. So first of all, the stability is really a first eigenvalue condition, right? It's an eigenvalue, but first eigenvalue is kind of invariant under taking covering space. It's a 2-sided stability is preserved under covering map. This is essentially because the first eigenfunction is positive, and it's the only eigenfunction being positive, essentially. Okay, so in other words, if we have a minimal immersion in Rn plus 1, you can lift this immersion to its universal cover, and the immersion from universal cover to Rn plus 1 is also going to be stable. Okay, so because of this, we're going to, without lots of generality, assume our manifold M is simply connected. Okay. And the second basic reduction we know, well, it's not a reduction, well, it's rather a property. So M has only one end. In fact, we know a little bit stronger property. So for any compact subset of M, K, the complement of it has only one unbounded component. So this was proved by Chao, Shen, and Zhu. There is a really nice explanation of this property, which I'll tell you later. But right now, let's just take it as it is. Okay. So I'm going to tell you the starting point of all the stories. That's actually our second proof of the theorem when n is 3. So all this goes back to I would say a miraculous computation by Gulliver and Lawson. So they did the following really great. Okay, I asked Professor Lawson there why they did it, but he said he can't remember. But anyway, they considered the following thing. So, okay, our goal is to prove, remember, that M is flat. So what we do is the following. So let's set R to be the Euclidean distance function to the origin. Okay, so then what we do is that we consider the and also let's assume the origin is inside M. Okay, so it's a minimal surface passing through a point origin, and then we consider the conformal blow up R to minus 2 times G. Okay. Now let's see what we're trying to prove. In the modal case, so if M is just a plane or hyperplane, then what this is doing is that it's changing a plane to a cylinder. It's then what I can say is that M, outside of the origin equipped with the metric G tilde, this is really just the unit Sn minus 1. A sphere, a minus 1 dimensional sphere of radius 1 cross R. Right. It's scaling all the concentric bolts to unit volume, to unit radius. All right, so somehow our goal is to prove that in general, if we assume M is a stable minimal surface, then after a conformal change, this looks like a cylinder. Okay, but now in what sense? Well, this is a big question. So, sorry, G tilde, exactly, yeah. Now we need to understand in what sense can we hope to prove the similarity between this conformal change and the cylinder. Okay. It turns out that the right notion is the so-called macroscopic geometry. So this means okay. So let me maybe try to write down a definition in this kind of related to the macroscopic geometry. So we say a metric space has finite, has Eurison k width. So it's just terminology called Eurison width, and k is an integer. So it has Eurison k width bounded by let's say lambda. If there exists a continuous map, let's say a k-dimensional simplicial complex, and the continuous map F from M to a simplicial complex, let's call it P, and the continuous map such that the diameter of each pre-image is bounded by lambda. Okay, so now it's a very general definition, but let's take k to be 1. Okay, so now let's try to play around with definition and see that this object here, the unit sphere cross R, has finite Eurison 1 width. Yes?
Briefly, when you say F inverse of P, is that the inverse of the entire?
Oh, no, sorry. Okay, X. For every X inside P. Yes. Okay, good. Yeah, that's sorry. All right, so let's real quickly see the fact that the example Sn minus 1 cross R has Euriston 1 width bounded from above by pi. Right? Why is that? Well, you can just collapse the entire spheres to a point, right? Basically, you just look at the projection map. Well, unit sphere here. By projecting onto the second factor. Now, the pre-image of any point here is just the unit sphere, which has a diameter bound. Okay? So so basically, what we want to prove here is that if your minimal surface is stable, then after the conformal change, it looks like a cylinder in the sense that it has finite Euriston 1 width. Okay, so go. So m minus 0 g tilde has Euriston 1 with less than or equal to, I don't know, 100. Actually, we need a little bit more than this. So in the definition of Euriston width, I asked that the diameter is bounded by lambda, but for the application to minimal surfaces, to the stable Bernstein problem, we also need to ask that the volume of the pre-image is bounded by some, I don't know, lambda 2. Okay, we need both diameter and volume bound of the pre-image. So, but again, this is satisfied by the typical example of the cylinder. Okay.
So enough to show finite Euriston width, or is there some concrete number that you
finite would suffice, but at the end we do have some concrete number. I'll write down. So, okay, so let me try to convince you that after this, if one can show something like this, then we're done. And the reason is basically because of the scaling. So pretend that we can, this is our m minus origin with the g tilde metric. So pretend that we can show something like that. Then in reality, what we do is that we find this. You take your manifold would have this manifold would have an exhaustion of surfaces. Again, look at the archetypical case is the cylinder, right? You have an exhaustion of these surfaces, which let's call it sigma k, which you pretend that these are the image of the geodesic balls or geodesic spheres before the conformal change. Okay, so before I have mg. And again, you look at geodesic balls, concentric geodesic balls. Okay. Now, they all have uniform area and diameter. But remember, the scaling between these two metrics is by the Euclidean distance, right? So a simple argument shows that if sigma k has bounded, uniformly bounded volume, then this tells you that the sphere, the boundary of the geodesic ball inside the original picture has, well, let's see, so some constant, well, the area of these things grows like rho to n minus 1. Okay? Just compare scaling. Now, there is a nice property for minimal surfaces. So
rho is, this is the radius in the original metric?
Yes, this is, exactly. So these are measured by g, so in g metric.
But in your picture, the horizontal axis is actually log rho.
Basically log rho, yes. All right, so then there's a very nice property on minimal surfaces, and that's called the isoperimetric inequality. So isoperimetric inequality on minimal surfaces tells us that, if you know the boundary of a region, bounded by the correct power, then the volume G of the entire ball is bounded by some probably another constant times rho to the nth. Okay. And then we're done because this is exactly the Schoen-Simon-Yau assumption we need to conclude the theorem. All right? I already raised it, but Schoen-Simon-Yau assumed this. So in fact, what we can prove is the following. So in fact, after assuming we can do something like that, then what we can prove is that if Mn immerses into Rn plus 1, then there's this constant, so volume G of Bm 0 rho is less than to the Cn times rho to the nth. And we can actually write down this constant, so because let's see. So C3 is this funny constant. Okay, I mean, they really don't matter, but just because some cloud you asked previously, I'm just showing you that they do exist. I mean, they're large constant and finite. Okay, so and I didn't check these constants. Really complicated, but as you can see from these examples. But just to give you a comparison, so actually the Pogorelov proof for the theorem when n equals 2 showed that a C2 is actually 4/3 pi. Much better, okay? So this is how he concluded the theorem in 2 dimensions. All right, so it all boils down to prove this kind of Urisohn width boundary in this this is some metric geometry property. So how do we hope to conclude this kind of Urisohn width bound? Well, there are some stories behind the Gulliver-Lawson conformal deformation that I didn't tell you. So actually, in the original paper, they checked the following property. So after the conformal change, the manifold satisfies the following. So all the geometric quantities are computed with respect to G tilde. So remember the stability inequality in the original metric reads this, right? So the gradient f squared minus curvature squared times f squared is non-negative. This is true for every f. But now if you do the conformal change and keep track of how these quantities change and the volume form changes, then one actually gets the following. So on G tilde, gradient square minus 1/2 times a scalar curvature square, scalar curvature times f square is larger than or equal to some positive constant times f square. Okay. Wonderful. So somehow the feeling is that, previously I got a 0 lower bound, and by Gauss curvature, the second fundamental form norm square, you can interpret it as any curvature, like including scalar curvature. However, somehow magically after the conformal change, there is a positive, strictly positive lower bound. This is what distinguishes between a plane and a cylinder. Okay, a cylinder has strict.
Is the scalar curvature the rescaled metric?
Yes, this is the scalar curvature of G tilde. Okay. All right. Now I need to quickly wrap up. So scalar curvature is the right curvature for the problem when n is 3. So this related to a question by Gormov. So he conjectured that a 3 manifold. Well, generally, if a manifold MNG has, let's say, scalar curvature larger than 1, then it's Urisohn n minus 1 width is less than or equal to some constant c just depending on n. Okay, namely, it looks like, microscopically, it looks like a minus 2-dimensional simplex. Okay, so when n is 3, this is exactly what we need. Okay, so this is true when n is 3. I'm not going to go into the details of this proof, but this was understood earlier, in some scalar curvature papers. Okay, and then if, for instance, if you want to do the Bernstein problem in R5, then n equals 4. But now immediately you see scalar curvature is not going to be the right quantity to control the one width, right? Right, because this conjecture predicts that the Eurozone 2 width would be bounded, but that's useless. We need a one width bounded. Okay. So really the thing that finally works is a basic observation. So
N is complete.
oh yeah, sure. Then the universal cover, let's say. Okay. Yeah. Or you can assume M to be complete. Yeah. Okay, so then really the upshot is that the right curvature, so the right curvature for Eurozone 1 width should be the so-called bi-Ricci. This would correspond to Eurozone 1 width. Let me let me quickly define what it is. So bi-Ricci curvature depends on two orthogonal directions, and that's just the sum of Riemann tensor involving either E1 or E2. Okay, so this was studied in a recent paper by Zim Brandl, Sven Hirsch, and Florent Zhang. So actually, there is an interpolation between Ricci and the scalar curvature. Bi-Ricci is the next, and the next curvature is C3, and etc. all the way. So R is actually Cn minus 1. So essentially, so each of these tensors are depending on more and more directions. Ricci depends only on one direction. Bi-Ricci depends on 2, and C3 depends on 3, etc. So they are just, by definition, the sum of all sectional curvatures that involves one of these directions. Okay, and we understand the Ricci curvature really well. There's Bonnet-Meyer theorem. If Ricci is larger than 1, your manifold is compact. If you think about it, its microscopic dimension is 0 because it looks like a point. Okay, the preimage of this point has uniformly bounded diameter and volume. So dimension here would be 0. And this bi-Ricci should be the next one and predicts that the dimension is 1, etc. Okay, and this one is Gromov conjecture. Okay, so let me just quickly write down the crucial computations that and theorems we proved. So the computation follows from the following. So again, in the stability inequality, A squared controls all the curvature, including the bi-Ricci one, if you like. So in reality, what happens when n is 4 is that still, let's take the Gulliver-Lawson conformal change. That lambda 1 of minus Laplacian plus, still everything computed with respect to G tilde. Okay. So, it's bi-Ricci positive in the integral sense, in the eigenvalue sense, basically. And from there, we could, there are other things to do, but essentially deduce this. Okay. And there has been an arms race extending this to the n equals 5 case. So Mazet really did the following. So in one dimension higher, something like this can't work. And in reality, he proved still in the conformal change, he took a combination of Ricci and bi-Ricci. And this is not 1 anymore. It's some positive number. And alpha, he needs to pick alpha really carefully, and that involves, some kind of computer assist, I believe. But anyway, numerically everything works out, and he could do something very similar. And last summer, I believe Tam wrote a paper claiming that one cannot use this approach to do the n equals 6 case. So for the one last bit of the open problem in the story, something new has to happen. Okay. I'll stop here.
I can answer the question.
Oh yeah.
You take a cone, standard cone, compact manifold, dr squared plus r squared times the manifold.
Right.
And you do this, you get a straight line across the manifold.
Right.
Defining product.
Okay.
It turns it into
Cylinder.
full line across. It's what you want. It's complete, and it's a product.
Okay.
That,
All right. Great.
that reason.
Yeah. Okay. Right. Thank you. Yes.
So in Pergeroff's paper on the two-dimensional case, does he actually do this kind of rescaling?
No.
His
Great question, but no. Actually, these practically any conformal change won't work because in 2 dimensions that condition is invariant under any conformal change. So you don't get any positive lower bound. He instead just use some test function, radial test function in the stability, and use Gauss-Bonnet to deduce the volume bound. It's quite different there.
So the meaning of this constant is slightly different in this.
Oh yeah. Exactly. It doesn't come from anything like that. Yeah.
Because I understand the point of the. Why is it so important that there is one with bring everything back?
Oh yes. Okay. So this has to do. Yeah. Okay. This has to do with the fact that all these surfaces are, the pre-image is contained in some annulus with fixed inner and outer radius. Claude explained. So this basically becomes log of the original distance. So if you know this thing has diameter bound, then originally, in the original picture, they lie between 2 geodesic spheres that differ by at most a fixed constant, right? So, yeah, that goes into partly goes into the isoperimetric inequality proof. Yeah.
Someone is concerned with what is threshold of dimension 7. Why dimension 7 is this threshold?
Well. It's a very hard question. You are essentially asking why minimal surfaces are regular in R7 below or singular in higher dimensions. I don't know. I think it's a philosophy question.
Gives counterexamples.
There are counterexamples, but why? That's nature's design. I don't know.
It's another question. Dimension 7, as we know. So
yes.
No relation.
I really don't know.
So there are also regularity results for minimal, stable minimal hypersurfaces and so forth that are related to this, that you expect them in high dimensions to have singularities, but if you're below dimension 7.
Yes.
So are there nice corollaries that would sort of use that? So you have you're sort of assuming differentiability throughout in the formulation of this.
That's right, yes.
In fact, you could, in low dimensions, you'll be able to make some statements about if it's a strict minimizer without any assumption about smoothness.
Yeah. Well, they're just all smooth. Stable in low dimensions are all just smooth. You're basically asking the Shane-Simon result. They prove optimal regularity for stable minimal surfaces in high dimensions as well. Well, those results are really useful for instance, if you want to construct minimal surfaces using min-max, for instance, then that's the result you need to use. You conclude you got an optimally regular minimal submanifolds on a closed manifold, but the regularity theorem really comes from those of the stable minimal surface.
So, are there any other questions? So I have one question actually.
Okay.
So what's expected if you have like a higher codimension? Like, are there any rigidities?
Yeah, great result. Yeah, there are some. So in higher codimensions, you can't expect anything like flatness because essentially, one observation is that if you have a two-dimensional minimal surface inside R, let's say Rn, let's say just R4, right? So well, it's another calibration argument. Any complex curve is minimizing. Yeah, you regard R for C2. So, for instance, you can have all kinds of singularities, right? Something like this. Well, the Bernstein theorem, the analogy would be to prove that the stable minimal surface, two-dimensional minimal surfaces in R4 are complex with respect to some parallel complex structure. That's done by Mikolov. On the other hand, we don't know, we don't have we don't know what is the local statement, like, global rigidity versus local curvature estimates. The curvature estimates there is still open, I think. It should be something like locally looks more and more like complex, but how do you quantify that? I think it's a question.
So any last-minute questions? Well, if not, let's
Thank you.